So the last thing that we're going to cover, new material tonight, is called a dot product. It's very, very easy, but there are a lot of nice little consequences that emerge from the concept of the dot product that really make it a powerful, powerful tool. All right, there's two types of multiplication when it comes to vectors. You have the dot product, and then you have the cross product. So tonight is dot product. Next class, we'll start off with cross product. All right. So when I'm dotting U with V, I'm taking the corresponding parts, so 3 and -1, and multiplying them. Then 5 and 3, and then 2 and 0. So corresponding parts get multiplied, and then you add the results. No, because the answer is going to be a scalar. Yeah, not a vector. Yeah. Yeah, it's going to give you the vector that is perpendicular to the first two vectors. So it will be an IJK. So we get a result of 12 here. All right. Maybe, I'm just thinking it's either, no, I don't think we have time for it tonight, but I will talk to you about what the hell this 12 means, because that's kind of important. But for now, we'll just work on the scale. All right. For number 2, it says find the scalar product. Scalar product and dot product are synonymous. They mean the same thing. So dot product. Say it again. Sine of u plus the sine of.
Or wait, plus the, is it like u multiplied by the sine of the angle?
That's part of it. That's another variation on the dot product formula, which we're going to get to. But if you're looking for the angle between two vectors, part of it has to do with the dot product. So that when you solve for the angle, you get it as a result of the dot product. But that's something else that we're going to get to in a little bit. All right. So 10 times -2 plus -4 times 1 plus 7 times 6. So whether it's in component form or IJK notation, it doesn't really make a difference. It's the same operation or a set of operations. If I can get my pen to work. So 18. All right, so computation-wise, it's not crazy. Now on your calculator, I think this falls squarely in the category of, yeah, it might be more trouble than it's worth, but I can show you really quickly just how you would handle a dot product in your calculator, and then you'll say, yeah, I'm not doing that. So you'd use squiggly brackets to input your vectors, 3, 5, 2, for example. And then another squiggly for -1, 3, 0. So what that'll do is that'll actually carry out the multiplication of the corresponding parts. And so at that point, it should be easy enough to just add them together with a little mental math. But you could also find the sum. So second stat, math 5 is sum of that previous answer. And it'll do it for you. All right. I kind of breezed through that, not because I expected you to necessarily remember every step. after I show you in the previous of periods of time, but because I don't expect you to do that. These calculations are not hard, so why do you need a workaround? You know? That being said, can't tell you how many times on a test, and we got like 12, what do we got? 3, 5, 7, 9, 11. Yeah, 12 people in here. So, yeah, like 8. Nah, that's too high. 6 or 7 people, about half the class, at some point, is going to think that 2 times 0 is 2. It happens every friggin' semester. Every time I teach this course. And only with the dot product. Multiply everything else by 0, no problem whatsoever. But for some reason with the dot product, 2 times 0 becomes 2. I have no idea why. So maybe you do want to work around. You know, because sometimes you need a second set of eyes on it. Because it's like, no matter how many times you look at it, 2 times 0 is going to continue to become 2 until you do something about it, you know? So.
2 times 0 is 20.
Or 2 times 0 is 20, exactly. What's 1 plus 1? 11. So the properties, commutative property of dot product and distributive property and things like that, they all seem very familiar, so I don't think you're going to have too much trouble with that, so I'm going to pop a nice little star there. In with, all right, because that's another thing. All right, so the examples here, we're looking at just applying the properties of magnitude, properties of dot product, I mean. So A dot B multiplied by C, right? So it's an implied dot here because we're looking at the associative property for the dot product. So if you look at it, if you just compare it to the first one, for example, or just the left-hand side of the second one, I mean, you could orient it so that the C is on the outside, on the front end, because of the commutative property. All right, commutative property of the dot product, but it's really commutative property of multiplication. It just extends itself to the dot product. All right, and that's telling me that I can regroup any way I want. All right, I can take the C and dot it against the U and then multiply the result, right? Or I can work on the inside and then dot it with the value on the outside. Now, normally a C represents a constant, and that's implied in the associative property because it does look like it's taking on the role of a scalar, but C is defined here as a vector. So we would actually think of this as C dotted against the result of AB, all right? So, but since the result of AB is going to be a scalar, it works itself out. So let's do A dot B. So 0 plus 4 plus negative 12 is going to be negative 8. All right. So then whether you do it in the form that it was originally written and say negative 8 against 5, negative 1, 3, or the alternate notation, because again, it's just the idea behind these questions is to familiarize yourself with the ways that it could be represented. You could look at it as 5, negative 1, 3 multiplied by the scalar negative 8. Either way, it's going to be the same thing. All right, so we're looking at negative 40, 8, and negative 24. In component form. It's kind of weird because when you're talking about a scalar product, the dot product and scalar product are synonymous, but the idea behind it is that you're always dotting something. So if I said, what's 3 times 5? You're dotting the two scalars, 3 and 5. All right? Just because they're not vectors doesn't mean you can't dot them. Right, which is why back in middle school, when they introduced the little dot symbol for multiplication, they said, oh, it's the same as the X symbol. Well, then why do we need the dot? The answer to that was, oh, so you don't confuse it with the variable X. And there's value in that, but really it's more so that there are two different types of multiplication, the dot product and the cross product. The dot product symbol is obviously a dot. The cross product symbol involves a cross, but in this case it's an X. And so what happens is, since it is two different types of multiplication in linear algebra Calc 3, we need to make the distinction between those two. But in middle school and high school, you're only multiplying scalars in most cases, hardly ever vectors. So from your perspective, there is no difference, right? Because scalar multiplication is just simple multiplication, right? But, you know, try telling a sixth grader that, oh, well, we're not using vectors here, so we want to use the dot symbol. But when we are using vectors, you use a cross symbol. And they'd be like, what's a vector? And then you go down that road, you know, so. Now, number 4 is the same idea, except you have a scalar multiple. So A, 1, 2, negative 3, dotted against twice C, 10, negative 2, 6. And so we're looking at 10 plus negative 4. Let me fix that. Plus negative 18. So negative 22 plus 10 is negative 12. And so that's not that bad. Not too bad at all. Now, b squared, the magnitude of b squared, you can look at this one of two ways. To see what did I do wrong?
2 times negative 1.
Ah, indeed. Wait, 2 times that? I thought I did that, no?
Yeah, you did.
So this is the 2c part.
It's fine.
Yeah, okay, yeah, this is good, and then this is the carrying out the next step. So that's right. Yeah, I think it's good. Now, magnitude of b squared, you can do that one of two ways. One would be to actually find the magnitude of b and square it. You have a program, or maybe you will. The video is online. Smash that thumbs up icon. Or you can take note of the fact that the magnitude of b squared is the same as b dotted against b. All right, so 0, 2, 4 dotted against itself. All right, and so we're looking at 0 plus 4 plus 16, and you get a result of 20. All right. So we kind of get a loose definition here of the dot product. Dot product of a vector in itself is the magnitude squared. So that's an interesting consequence. When you think about what that could possibly mean, you start getting into the visuals of it. And so that's what we're going to talk about in a little while, because the dot product helps us to determine the component of one vector that's acting in the direction of another. And so it's kind of a weird thing to think about, but I have diagrams and explanations to go for that, or to explain all of that. All right. So, but the simple idea is that if two people, for example, are carrying a couch up a flight of stairs, there's an idea that, well, they're either both pulling their weight, you know, like doing their fair share of the work, or one person is a little lazy. I mean, if you've ever been in a situation where you're carrying furniture up or down a flight of stairs, you probably said, either in your mind or out loud, yo, are you actually doing anything? Or wait, I feel like I'm carrying this thing myself. Like, are you sitting on it or something? Like the thing is like a couple 100 pounds, but I feel like I'm carrying a ton. Like, what's going on here? So you would think to yourself, if I am putting more exertion into it, then that would require them to potentially put less exertion, depending on the nature of the object. If it's a couch, it doesn't matter, because you still got to lift it. Right? But if it's, let's say, like a narrow dresser, you know, like if you put more effort in, they can potentially put in less effort. Now, if you're both putting equal amount of effort in, then, but there would be an amount, you'd be more than the sum of your parts, because there would be the idea that, okay, I can lift 1,000 pounds because I don't have to lift 1,000 pounds by myself, all right? Their work is contributing to my work, and my work is contributing to their work, and we both can do subsequently less based on the balancing act of the effort, all right? So that's what a dot product helps us to determine, right? The idea that you can actually have one person, you're working in the realm of force, one person contributing to the amount of force or lack of force that another person needs to apply to a given situation. And pushing a car down a road, things like that. All right. So that is not the eraser. Got a nice little proof here. Let's see if I can. Because I changed the size, I can't now erase that star, and it's going to bother me for the rest of my life. Let me do this. Thickness. Also, I can imagine the counter and the toolbars is kind of distracting. All right, so we're going to prove this relationship u dot v is equal to the magnitude multiplied by the angle in between. But it gives us a nice little consequence, and that's the cosine of theta is equal to the dot product of u and v divided by the magnitudes multiplied. All right? So,
Just go over again and tell us how you got v minus u, just graphically. I mean, how the vector goes from.
oh yeah, sure. Let me change the size of the marker first. Okay, so we have u and v, but if I wanted v minus u, that's the same as saying v plus negative u. Oh, that's too thick. That's disgraceful. V plus negative u. So what I need is a negative u. All right, so that's what I'm going to do. I'm going to snag a u. That's poor quality u. Try that one. Bring it in the negative direction. Come on, get over there, you son of a gun. All right, so that's my negative u. So if I want the vector sum of v and u, I'll also need a v to create my parallelogram. And again, I like the parallelogram approach, so it is what it is, but that's the way I operate. All right, so here's my v. I'm going to get another negative u in there. That is not the line draw tool. To create my parallelogram. Now the vector sum is going to be this diagonal. V plus negative u. Now, because opposite sides of a parallelogram are congruent, it turns out what I did inadvertently, but it was a nice or a pleasant surprise, a happy accident or whatever. This creates also a parallelogram. So these two sides would then be congruent as well. All right, so that justifies why we can call this v minus 2. All right, so it's a little bit roundabout, but it gives a nice little justification. All right, so let me see about a little shading here. The fill, just make it green with a little less opacity. All right, let me try this. Could not match its shape? What's wrong with you? It's a triangle. Pen turned off. There we go. That's the triangle we're working with. So when I'm looking for sides of a triangle and I know it's not a right triangle, I think of things like law of sines, law of cosines. So in this case, I have, well, only one angle. Yeah, you could talk about like 3 sides and included angle, things like that. But if you have 2 or more angles, it's law of sines. If you have 1 angle or less, it's law of cosines. So the more popular version of law of cosines, c squared is equal to a squared plus b squared minus 2ab cosine c. All right, so the angle here, theta, I'm going to designate that being at vertex C. The other 2 vertices, I don't care what's what. One's A, one's B. All right. Sides opposite a given angle have the same name, just with a lowercase. So the V minus U is the C, the U is the A, and the V is the B, the lowercase A, B, and C values. So I'm going to write V minus U squared equals U squared plus V squared minus 2UV cosine theta. Now there's one little issue with this, and that issue has to do with the fact that, how do you square a vector? All right, just a vector. Well, it all depends. Right? And the issue that comes into play is that, well, why would I want to square a vector? These are lengths of sides. So what I would want to do is square the magnitude of those vectors. All right, so I'm going to make a slight adjustment here and write this as the magnitude of V minus U squared is equal to the magnitude of U squared. So magnitudes across the board. All right, and again, the rationale behind that is a vector has magnitude and direction. When I'm talking about a length of a side, I don't care about the direction, I care about only its magnitude. So only care about the length. Now, on the left-hand side, we have the V minus U magnitude squared, but we also have a nice little relationship that we kind of played around with on the previous page, and that is V minus U squared is the same as the dot product of V minus U. All right, so I could make that adjustment. All right, so just ordinary algebra, distributive property, V squared minus 2UV plus U squared. That's going to be equal to the right-hand side. All right, now these again are dot products, all right, because I'm dotting the 2 parts together. So this is really the same as V dot V minus 2U dot V, poor quality V, plus U dot U. Still equal to the right-hand side. Now, another thing that comes from what we played around with on the previous page is that the dot product of a vector in itself is equal to the magnitude squared. Now, normally I wouldn't look to make that adjustment, but I noticed that on the right-hand side I have magnitude of U squared, magnitude of V squared. If I could transform these 2 guys into magnitude of U squared and V squared first, then they'll cancel out. U squared. And now I'm just going to rewrite the right-hand side. I know it's annoying, but. So part of the challenge is knowing when you can transform from one form to the other. But all of these are now gone. So -2 u dot v is equal to -2 magnitude of u magnitude of v cosine of theta. And so we can wipe out the -2's, and now we have our rule. The dot product of u and v is equal to the magnitudes multiplied by the cosine of the angle between them. All right, so it's a pretty chunky proof, but it's rooted in stuff that is either given or something that you're fairly familiar with. Right? Now, the question that would naturally be in play, I think, and I experienced this myself, is how would I know to use the law of cosines here? Now, eventually you got to kind of settle in on those sorts of things, because it's like, well, it's not a right triangle, so it's law of sines or law of cosines. Maybe you thought it was law of sines. If that's the case, you'll find out pretty quickly that it's not. All right, and that's all right too. The thing is, you know, like when I do these kind of proofs, I try to put myself in the shoes of the person who came up with it the first time. Now, there are plenty of people out there that can look at this thing and say, of course, I would use the law of cosines immediately. But then there are people that would be like, well, I don't know, let me try this. If it doesn't work, I'll try that. You know, and so a lot of the discoveries in math came from things just along those lines. Right. Applying this information is not difficult, though, because we're looking to find the measure of the angle between the pair of vectors. So the ancillary formula, if you will, so cosine theta is just really what you would get if you solved the original formula for cosine theta. You could solve it for theta if you want. I just find that's a little too much of a pain. Is equal to the dot product multiplied by the divided by the magnitudes multiplied. All right. So finding the magnitudes, that's going to be the important piece here, because the dot product is not challenging. All right. So I'm looking for, and I'll because the formula's got u's and v's, I'll call this part u and this part v. So I need dot product of u and v. So 2 plus -1 plus -3. All right, just multiplying corresponding coefficients and adding them together. So -2 as a result. I need a magnitude of u. That's going to be the square root of 1 squared plus 1 squared plus 1 squared, so square root of 3. You're not going to need a fancy program in your calculator for that one. Magnitude of v, 2 squared plus -1 squared plus -3 squared. So 9, 10, so 14. So popping it into my formula, I would say cosine of theta is equal to -2 over the square root of 3 times the square root of 14, which is the same as saying -2 over the square root of 42. So we could solve for theta pretty easily. You just hit inverse cosine on your calculator. Just make sure you're in a reasonable mode. Radian or degree, it doesn't matter. Just if you get a radian answer and put a degree symbol on it, that's going to be a problem. So I'll do it in degrees. I just put my calculator in degree mode. So second cosine, this one, it's basic trick, so I'm just going to talk you through it. So -2, inverse cosine, -2 over the square root of 42. And I'll write down what I typed, and it's about 108 degrees. So in your calculator, you would do inverse cosine of -2 over the square root of 42, and you get approximately 108 degrees. For these kind of questions, it really doesn't matter, again, which form you go in. You just need to be prepared to go either way. Like, you need to know the relationship between radians and degrees, but for contextual situations, and this is not one of those, but it could be, you know, like a boat's going off in a vector this direction, a plane's going off in a vector that direction. What's the angle separating them? Like, people think in terms of degrees, so there's no reason why you can't put your answer in degrees. But you should have a sense of what that corresponds to in radians. All right. So the next one, same idea. We need the dot of u and v. So again, just call one u and the other one we'll call v. So -4 plus -20 plus 24. All right, so that one gives us a clean 0. All right, so the magnitude of u and v are irrelevant as long as neither is the 0 vector. All right, because if one of them is the 0 vector, then the magnitudes would multiply to equal 0. So the bottom of the fraction would also be 0. So we have the dot product of the 2 on top, and then the magnitudes multiplied on the bottom. 0 on the top is fine as long as there isn't also a 0 on the bottom. We don't want indeterminate. We don't want undefined. And besides, how are you going to find an angle between two vectors if one of them is a 0 vector? You're not going anywhere. So it would just be a linear distance, all right? So what we're getting here is cosine of theta. I'll do that in purple, actually. Is equal to 0, which means theta has to be equal to what? 90 degrees, all right? So what we get is the definition of orthogonal vectors. The non-zero vectors u and v are orthogonal if and only if the dot product of u and v is equal to 0. Right? Because if the dot product is 0, they're separated by 90 degrees. All right? So orthogonal vectors are separated by 90 degrees. Keep doing that. All right, so that's not bad. So basically it's perpendicular but expanded into additional dimensions, so not just in two space. Basically, you've been working with orthogonal lines and things like that for years. It's just you've been calling them perpendicular because the word perpendicular only refers to two-dimensional relationships. Now you can look at something that exists in a three-dimensional system in a two-dimensional fashion. You just got to look at it from the right angle. You know, so if I have two vectors that are just kind of floating there in space, but I turn my perspective so I'm looking at it from a side view, then I'm looking at something that's in 3D two-dimensionally. All right, so from that perspective, it's perpendicular. But if they're just kind of floating out there, then I would call it orthogonal. All right, so that's more of a conceptual thing. Mechanically, it's just a matter of determining if your dot product is equal to 0. All right, so P dot Q is equal to 10 plus 0 plus -10. Result is 0, therefore orthogonal. put a little exclamation point. I'm very enthused about that. I always put a question involving this concept on the test. It's like the gimme question. But you know what happens? It's just people forget this relationship, and so they get it wrong. When really all you have to do is show that the dot product is equal to 0. Right? So, you know, don't lose sight of this, but it's not difficult, so you shouldn't anyway. All right, so I'm gonna pop a star on these bad boys. And then we're gonna talk about the component and the projection between two vectors. Vector projection of V onto U is the vector labeled proj sub U of V. So it's V onto U. Now the notation kind of suggests that, because you kind of look at it as the subscript is U, so that's the one that is below physically in the notation, below the V. So if one is going to be on the other, it would make sense that the one below would be the one that's onto, or being put onto. It has the same initial point as U and V, in the same direction as U, and represents the component of V that acts in the direction of U. All right? So, cool, a lot of words. If theta represents the angle between U and V, then by properties of triangles, then by math, we know that the length of the projection of V upon U is that. When expressing cosine theta in terms of the dot product, this becomes, oh, look at all that wonderful stuff. All right. I didn't understand any of that when I first saw it, and I don't even think I understand any of that after just reading it now. All right, because that's textbook language. All right, my job is to interpret the textbook language so that you have a fighting chance of understanding it. So what I'm going to say here is, put it in simple terms, going back to the two people carrying a piece of furniture up and down the flight of stairs. You have a vector going up in one direction, a vector going up in another direction. They're both contributing to the movement of whatever this object is in this general direction, all right, in the northeast direction, all right? But how much of V is acting in the direction of U? That's what a projection of V upon U is talking about. The other way around would be, I'm going to redraw the picture, just kind of right next to it. Just make sure I do it correctly. Oh, look how shaky that line is. Oh, I didn't put the line draw tool on, so. Classic Bob. Yeah, me too. All right. So, again, I have V and U. Now, if I dropped an altitude going from V to the extension, I'm sorry, U to the extension of V. So I'm going to shoot V up in this general direction. It's going to look something like that. This whole segment going from here to here. So it's beyond, get that, beyond what V is actually doing. What I'm getting is the projection of U upon V. Okay. So basically what's happening here is it's an imbalanced situation, right? Because U is actually contributing more in the direction of V than V is, right? Because if I draw this altitude, I create a right triangle out of it, this is how much, this blue line here, this blue ray actually, is how much U is contributing in the direction of V. And this one is how much V is contributing in the direction of U. You can see based on the blue diagram that U is contributing more to the direction of V than V is itself. All right, so, I mean, I could think of a few examples off the top of my head, but the first one that comes into mind is money. So, kid graduates college, doesn't have enough money to go out on their own, so they live at home with mom and dad. So they're making $500 a paycheck, but their student loans are amounting to, let's say, $2,000. So the kid is contributing, let's say, because they're not going to dump all their money into it, they got to live, kind of. So they contribute $250 per paycheck, so $500 a month to their student loans, but the parents are picking up the other $1,500. How nice of them. All right. That's high school. I'm still paying off my student loans, so I don't know what it feels like to have parents pay for my student loans for me. My wife will be paying off her student loans, I think, until after I'm dead. And unfortunately, I think that's true, because she's like got a solid 30 more years, and her student loans actually cost more than her mortgage. So it's a lot of strain on the heart. So I'm only 41 right now, but you tack on another 20 to 30 years, yeah, you know, with that kind of pressure, I don't know how it's gonna play out, but we'll see.
What college you went
What's that?
to? What college you went to?
NYU.
Oh.
It was so cheap back then. It only cost $35,000 a year.
What?
Yeah, that's nothing. Mere peanuts, you know.
70 now?
70 now.
70.
And you know, honestly, I don't look at 35,000 as being cheap, despite what I just said, because I'm still paying it off. Like, that's the thing. I'm still paying $400 a month. And the crazy part is, I have full ride for undergrad. My student loans is all exclusively grad school, because they didn't give the same kind of scholarship for grad school that they gave for undergrad. And so that's that, you know. My wife went to law school. Different story altogether. Yeah, and you know what, that's the thing, like, I don't know if anybody's ever been to Disney World during peak season. Like, what happens is, you get to the gate, and if you don't get there early enough, the park is packed. So what they say is, we're at capacity. You can't come in. All right? We gotta let people come out before you can go in. And they do that. It actually goes pretty quickly, because people leave. And I think they leave not realizing that it's gonna be hard for them to get back in. But they leave, and then you can go in. Right? I think they should do that with professions. Like law school, for example. After the recession hit and everybody started losing their Wall Street jobs, everybody went to law school and saturated the market.
And now
so,
you always see commercials for lawyers.
There's an
everywhere.
access, yes.
now there's plenty of lawyers, but not enough jobs for those lawyers. And so what should happen is the colleges, they should look at the market and say, yeah, we could teach you to be a lawyer, but there's not gonna be a job for you. So we're gonna max out, okay, we're only gonna take, like, I don't even know what the numbers are, but let's say they normally would take 100 incoming law students, which is a low number. We're only gonna take 20 this year, because we don't wanna put you in a position where you have all this debt, but not have a way to pay it off. I think that would be great. The problem is, there are people, you know, the sense of entitlement, which is like, but I want to be a lawyer. I want to be a doctor. It's like, well, but we're not going to let you because you're not going to get a job. Like, we're not going to let you throw your life down the tubes. Unfortunately, my wife got a job, so that's great, but I don't know too many jobs that allow you to pay off an extra $1,500 a month in student loans. So between the two of us, it's $2,000 extra. That's more than the mortgage. It's crazy. Right? So yeah, I would love to have had a parent that was willing, able and willing to pay all this stuff for us. But this is the black line here is the starving college graduate, the blue line is what the parent is paying, and you can see that the parent is actually contributing more to the college grad's future than the college grad is themselves. All right? Maybe back in the 80s it was the other way around. Right? 80s, 90s, I don't know. All those folks seem like they're out of debt, so.
It was cheaper back then,
Yeah, everything, yeah.
and SUNY keep it for
Houses,
free.
geez.
Houses were cheaper, but the money was expensive. You get a $100,000 house, but you're paying 25% of the mortgage. Now it's $400,000 for the house and 4%.
Right.
Trading off.
Yeah, that salaries were a lot less than.
It cost them
And
a lot.
yeah, cost
Yeah,
of living,
totally.
food, everything was cheaper.
Yeah, everything. Yeah, so that's the nature of it, but at the risk of doing more math, I think it's probably a good idea because I'm starting to get really depressed again. So anyway, so that's the conceptual representation of the idea of projection, and I think it's a valuable idea. So if you come up with a vector that represents the concept that you're interested in, then finding the projection could give you some really valuable information, right? Now you might look at it and say, well, real life isn't a straight line. We're going to learn about vector valued functions, and those are curves of differing varieties, and we can apply these concepts to those curves. So pretty cool stuff. All right, so how do we get this formula though? Well, I'm going to go back to this diagram. We got a value theta. This is my magnitude of V. All right. And so I'm looking for the projection of V upon U. So I could say just simply, using good old-fashioned SOHCAHTOA, SOHCAHTOTALY, as Mr. Panzer would say, cosine of theta is equal to the adjacent over hypotenuse, the projection of V upon U divided by the magnitude of V. Now the thing is, that projection of V upon U, that's a vector. Cosine ratio, sine ratio, whatever, they're all dealing with lengths of sides, so I'm going to slap a magnitude on this. All right, so what I get is that the magnitude of the projection of U upon V is equal to the magnitude of V multiplied by the cosine of theta. All right. What we did, all us mathematical geniuses out there, not me, the person who invented this, they said, okay, well, I'm not writing that every time, so we're going to call this the component of V acting in the direction of U, which I think makes perfect sense in terms of the name. The notation of it can be a little, I don't know if I like that one very much. But what we can do then is take, so this leaves us, I'll just draw an arrow here because the rest I can just talk you through. The cosine of theta, you're like, oh, where'd that come from? See the previous page where we invented that rule. Cosine of theta is the dot product of U and V divided by the magnitudes multiplied. So that if you clean it up, what we get here is that the projection of U upon V, I'm sorry, V upon U, is going to be the dot product of U and V divided by the magnitude of U. All right? So it's really as simple as that. The projection, the magnitude of the projection is what I meant to say. All right? So that'll give you a component value, but a numerical scalar. All right? So that tells you the quantity. So in this case, it would tell us how much the kid is contributing to the parents. All right? So the kid's paying rent maybe, or that maybe they're picking up the cable bill or something like that. So that vector would represent how much the kid is contributing towards the parent's future, whereas the other one would be how much the parents are contributing towards the kid's future. All right? So this is the actual quantity. Now, if I wanted to determine the projection itself, then all I have to do is multiply this by a unit vector. All right. So projection of v upon u defined the actual vector projection of v upon u multiply by a unit vector in the direction of u. And that's specifically because it's v upon u. How much is v contributing to u? So I want to actually determine what it's gonna be in the u direction. So that's why we multiply it by the unit vector in the direction of u. All right. If it were the other way around, if it was u upon v, then I would multiply it by the unit vector in the direction of v. So we have a formula. There's nothing wrong with just using the formula. You don't have to invent it every single time. So u dot v, -3 plus 20 plus 3, it's going to be 20. All right. Vector u is vector u, so I just need the magnitude of u squared. Now the magnitude of u squared is the same as dotting u against u. I prefer to do it that way just because I feel like it's less thinking. And if there's one thing I like, it's not having to think. All right, so 1 plus 16 plus 9. So we're looking at 26. All right. So what we have is 20 over 26 multiplied by vector u. So the projection of v upon u is going to be 20 over 26 in the direction of u, which is -143. Simplify 10 over 13. And then run it through the mill, you get -10 thirteenths, 40 thirteenths, 30 thirteenths. I'll put a star on the next one. Actually, the next two. A little word problem there for you. I've had people ask in the past, can we just leave it like this, 10 over 13 times -143? And I say, no, I want you to distribute it through. They say, why? And I say, because I freaking said so. And then that's the end of it. So I just figured I'd save us all from that conversation. Make it easy, right? This is the way I want you to represent the answer. That's all. Okay. Yeah, are they equivalent? Absolutely. Is one better than the other? Hell if I know, right? So, but that's just how I want you to write it. This is one of the very rare instances where I have a particular preference. This is one of them. So, but anyway, just kind of going back to this setup here, I just wanted to talk very quickly about how this formula came into being, because the first piece of it is, so the v multiplied by u dot v over, that's all the part where you're coming up with a component. This last little bit here, this guy right here, is the unit vector. in the direction of u. All right, so just a quick review, because again, either I forgot to go over it or I went over it a while ago. Unit vector, all you're doing to determine a unit vector is dividing a vector by its own magnitude, all right? And so that's just giving you a vector with a unit length of 1 in the same direction of the given vector, all right? So what it does is it allows us to develop a basis for a particular system, all right? So I now know what the vector would be in the direction of u for this system that has a magnitude of 1, all right? So if I were to carry this out through the magnitude process, whether it's by hand or in your calculator, that's going to give me a magnitude of 1, and that's the whole point. Or 1 multiplied by the component is what I mean to say. All right, numbers 12 and 13, well, 12 is along the same lines as 11, except it's in 2 space, so it should be easier to do. Number 3 looks like it would be a lot harder, but it's actually not that bad. It's just, you throw words into a problem and people start freaking out. So by all means, freak out and either do it or don't do it, but we'll go over it next class. But I want you to at least attempt, or I suggest, recommend that you attempt it first before I just take you through the process, because I don't want to steal all the thinking moments for this kind of question. Let you kind of wrestle around with it first before I give you the short way. So the last thing we're going to do tonight is called a cross product. It's pretty crazy stuff. And in fact, the derivation of it involves a system of equations. It's really quite incredible. I'm just going to give you the basics of it. We're not going to go through the whole thing, the whole derivation, which also means that you're not going to be responsible for the derivation on the test, just because it takes up like a whole page of your notes if you were to do it out completely. But I want to give you a sense of what the setup is and how you would go about the process. What a cross product will give us, and by the way, next class we're going to merge ideas, dot product and cross product put together, which is going to give us something known as a triple scalar product. Very exciting stuff. Also known as a determinant. All right, so a little connection between linear algebra and this course. Anyway, cross product, you start off with 2 vectors. What it'll do is it'll give you a third vector that's orthogonal to the other 2. So if I have 2 vectors going out in space, the cross product is going to give me the third vector. Now that third vector could be going, based on this, upwards, or it could be going downwards. All right? So either way, it's going to be perpendicular or orthogonal, depending on your perspective, to the original 2 vectors. All right? So orthogonal, well, that sounds an awful lot like a dot product. What this is telling me is that u and w, so I can just draw a quick sketch, really. Here's u, and here's v. So there's some w that's coming off of the intersection between these 2 vectors, such that it's perpendicular to both.
What about going the other way?
It could go the other way, but I'm just going to draw it this one way. But it could go downward also. All right, so what we're going to get through this process is 2 different vectors, but generally we just need one of them because the other would just be the negation. All right, so once I find one negated, I have the other. All right, so as long as you could learn the technique for finding one of them, you're in good shape. So this is my W. Purple is. So using a dot product, I would say U1, 2, and 3 dotted against W1, 2, and 3 is going to result in a value of 0. All right, because one of the things we learned earlier is that the dot product, if it's equal to 0, the two vectors are orthogonal to one another. All right, I can distribute this out using the dot product. U1 W1 plus U2 W2 plus U3 W3 is going to be equal to 0. But I also have V1, V2, and V3 dotted against vector W. That's also going to give me a 0 as a result. So V1 W1 plus V2 W2 plus V3 W3 also equal to 0. All right. Now, ultimately, what we're looking to do here is figure out what W1, 2, and 3 would be in terms of U1, 2, and 3, and V1, 2, 3. All right. So through all of this mess, what I'd have to do, it's kind of terrifying when you think about it, but I'd have to solve this for W1, 2, and 3. Because that's going to be the cross product. That's the definition of the cross product. And you can see, I mean, it's a mess. Because we have to use substitution. Solving, pick a variable, it doesn't matter. Like solve for W1, for example, and replace the W1 here with that. Simplify, clean it up, see what you get. Hopefully some other things would cancel out. Because you're going to be replacing a W1 with a W2, W3, so you should be able to consolidate some things. All right? Maybe you have to do an additional substitution. It gets pretty crazy. I'm not exaggerating when I say that it's an entire page of your notes to carry out this process. All right? But just the setup is all you really need in order to understand that this is something that will work. Because ultimately, if I'm solving for W1, W2, W3, it's going to give me expressions that are in terms of U1, U2, U3, and V1, V2, and V3. All right? So this first piece here is the same as my W1. This piece here is my W2. And this piece here is my W3. Now, one part of it that you may not feel 100% comfortable with is the sign change component. The W1 in the cross product is always represented as a positive. W2 is the negative, and W3 is going back to positive. It's alternating in sign. That actually has to do with permutations, so thinking back to probability and statistics and things like that. The different ways in which you can arrange the elements of these vectors, it bears out that some permutations are considered to be positive permutations and some are negative permutations, depending on the way it's arranged. And so that's a whole other explanation and concept. So I go through that in my linear algebra course. I believe I'll be doing that in tomorrow's linear algebra class. So yeah, so if you want more on that, you can check out that video. Right? So you just gotta go to my linear algebra class list or playlist. I mean. Right? So I'll talk about the right-hand rule in a few minutes once we do the computations, but it's actually pretty easy. There's a nifty shortcut to help us determine the cross product. I'm going to take you through that because writing it this way, I mean, it's fine, but then it's very easy to get crossed up, no pun intended, because you look at it and say, okay, well, which one's U2 and V3? Ah, crap, what am I looking at here? But if you use what we call cofactor expansion, also a linear algebra technique, it does kind of give you a little bit better of an idea of how this is going to play out. So what we do is we arrange our vectors as row vectors. All right. So you can, in a matrix, you can represent your vectors vertically or horizontally, as long as you're consistent, and each way will have different meaning. This part is kind of weird. I, J, K are actually vectors themselves, so you actually have a vector within a vector. That's strange, but that's a different conversation, again, for a different day. So what we do in order to determine the I coefficient is identify the I row. All right. When you identify the I row, what you're going to do is you're going to take the elements of I row and column. You're going to take the elements that make up the matrix that are not in that row or column. All right. So basically, I'm just crossing out the row and column that I exist in, and then just creating a matrix out of that. All right. And I'll show you how to handle that in a second. But then for J, I'll do the same thing. I don't want to mark up this diagram too much. I would cross out the middle column and the top row, and I'd be left with U1, V1, U3, V3. All right, so that gives me that one. And then the same thing for K. If I wiped out the row and column that K is in, I'd have U1, V1, U2, V2. Right? So that's where these entries are coming from. So really, as long as you know to set up your matrix this way, then these are going to build themselves, all right? And then it's the question of what do we do with that? So I'm going to take you through an example and you'll see, all right? So we're finding the cross of P and Q, sorry. I, J, K, undo. -1, 2, 5, 4, 0, -3. All right, so I'll use a highlighter here. So I'm looking for I. So I'm going to wipe out the row and column that I is in. So, and then turn my highlighter off. 2, I might as well go blue. Those keeping score at home. And I'll do the same thing for J. So -1, 5, 4, -3. And then I guess red. So same thing for K. -1, 2, 4, 0. All right, so to find, we're looking for a determinant here. The vertical lines around a matrix is looking for the value of the matrix. It's asking for the determinant. You do it one of two ways. In your graphing calculator, or diagonal down minus diagonal up. For a 2x2 matrix, it's easy enough to do by hand. What I mean by diagonal down is multiply, starting from the upper left and going to the right. The diagonal going downward, multiply those two values, and subtract from that the result from when you multiply the diagonals going up. All right. For anything other than a 2x2 matrix, that process won't work. But if I'm looking for the cross product between two vectors in free space, it'll always be a set of 2x2 matrices. So this technique will work. If you don't want to do that, that's fine. You put it in your calculator. There is a determinant function. The problem is you're putting in 3 separate matrices in order to find the determinant, and that's kind of annoying. All right, doing it once or twice is okay, but once you hit the third time, you're like, and especially if you have a bunch of problems to do related to it, it could be kind of nightmarish. All right, so the diagonal down values, -6 minus 0, those are going to be the coefficients of I, minus 3 minus 20. Diagonal down is -1 times the -3, which is +3. 4 times 5 is 20, subtract the 2. Plus, diagonal down is 0, minus 8. And that's the K. I missed the J. And there's the K. All right, so we're looking at -6I. 3 minus 20 is -17. Negative, negative, so plus 17. Minus 8K. Or you could put it in component form. You could write it as -6, 17, -8. Either way. Oh, I think I see what the problem is. Here, browser. It definitely is. All right, so that is the relationship. All right, and I'll show you where that comes from in a minute or two. Number 6, my tendency would be to go the other way, because I look at it as and say, okay, in order to find theta, I'd have to first find the angle. In order to find the sine of theta, I have to find the angle between these two vectors, which may or may not be easy. And then after that, I got to use this formula by finding the magnitude of each of these. So at this point, I'd be like, you know what? Let me just do the cross product. So I, j, k, 5 to -1, 0, -1, 4. All right, so you're adapting to the situation, is really what it comes down to. All right, so for I, again, I'm ignoring the I column and the I row, so 2, -1, -1, 4. And then maybe as you go, run your calculation so you're not overwhelmed with it. All right, so this is going to be 8 minus a +1, so 7I. Ignore, for the second one, ignore the J row and column, so 5, -1, 0, 4. So that's just a 20, right? Because on the diagonal up, 0 times -1 is going to be 0. So diagonal down is 20, so minus 20J. And then for the K, ignore the K row and column, so 5, 2, 0, -1. So again, we have a nice looking 0 in there, which means the diagonal down is the only thing I'm caring about, so -5K. All right, so that's the cross of A and B, or U and V if you want that notation. All right, but this one's a little weird because it's not saying find a vector orthogonal, it's saying find a unit vector orthogonal. All right, so what I need is the magnitude of A and B, A cross B. So 49 plus 400, so I'm squaring each, plus 25. So 474. And so the unit vector is going to be A cross B over the magnitude of A cross B. Can I simplify the rad 474? I don't know. Maybe. I don't want to, so I'm not going to. And I'm going to put it in component form. So rad 7 over rad 474. -20 over rad 474. Now, just for clarification, if it was the square root of 25, 625 even, you know, like something that's a perfect square and you know it, yeah, get the result. But 474, it could be, maybe it's not. but this isn't a computational skills course, so I'm not looking to take off credit for funky radicals not being simplified. All right, but one thing you can do if you're not sure, and again, this goes back to that program in my linear algebra course that I posted for magnitude. Maybe you write that program because a unit vector should have a magnitude equal to 1. So pop these values into that program and see if it gives you a magnitude of 1, because if it doesn't, then you did something wrong, because it's not a unit vector unless its magnitude is equal to 1. All right, so the last thing we're just going to take like 10 seconds. That's an exaggeration. I'm just going to talk to you about where that area of the parallelogram business comes from. So we locate vectors u and v such that they form adjacent sides of a parallelogram, kind of like a vector sum. Find the area of the parallelogram given by the magnitude of u and v, or u cross v. All right, so the derivation is very easy because area of a parallelogram is base times height. All right, and I labeled everything in the picture for you. All right, because these are vectors u and v, but we need the magnitudes if we're talking about the length of sides. All right, so the theta part, if I needed the height, I'll just call that h. Sine of theta is equal to opposite over hypotenuse. And so that actually gives you v times the sine of theta. So h, which you define as your height, is really the magnitude of v times the sine of theta, just by knowing simple unit circle trig, SOHCAHTOA kind of stuff. All right. The length of the base is equivalent to the magnitude of u. The height is the magnitude of v times the sine of theta. So as it turns out, we have a proof that demonstrates that, yeah, that formula that we're using to and defining as the magnitude of the cross product will also give us the area of a parallelogram, right? In 2 space, 3 space, or 10 space, it doesn't matter, all right? So I'm gonna pop a couple of stars, and that's it. That's why I said it would take like 10 seconds. I'm gonna pop stars on 7 and 8. And that's where we're gonna leave it for tonight.